work with the stellar mass functions in Go Green.
Unmuted, yes. Thanks a lot, Michael and Adam, for very nice appetizers and showing in general what we can do with Go Green.
We don't see your slides here, Remco. You don't see my slide. I see your desktop background, which is beautiful, but I don't see your slides. There, that's better. Yeah.
All right. So I'm going to talk about measurement of the stellar mass function of Go Green, and this is really work that is possible based on the whole data set. So based on all the spectroscopy and photometry. I just want to highlight some key people that contributed to this work. Really a lot of work over the last more than 5 years now. So for those of you who don't think about stellar mass functions every day, just to give you a rough idea of the motivation of studying stellar mass functions. First of all, what I always like to think about is how self-similar dark matter really is. So what I show you here are two dark matter halos with very different mass, and they look essentially the same. So they're shown at different spatial scales, of course, but if I would not have shown you the mass of the different systems, you would probably not have guessed this correctly. On the other hand, if you look at galaxies, of course, there is a characteristic mass, which we call the characteristic mass of the stellar mass function. And that sets the scale of galaxy evolution. And by studying the stellar mass function, going out and actually measuring stellar mass function in different environments and in different redshifts, we hope to understand what sets the scale, which first of all shows that star formation in general is very inefficient. So even at the peak of efficiency, they're well short of the cosmic baryon fraction. And in the low and high mass end, there's even lower efficiency. So that's what we call galaxy quenching. And indeed, the difference between the theory, so if all baryons would have formed into stars, equally spread in dark matter halos, at low and high mass end, there is a clear difference between these observations and such a very naive theory. So measurements of the stellar mass function are absolute key to understanding how galaxy evolution works. And this is one of those measurements that I would like to highlight. There are many others also in this field. So this is a measurement from Adam a couple of years ago now, where you can see on the left the total galaxy population increasing from redshift 4 to the local universe. So this is the total stellar mass content building up. But if you split this by galaxy type, quiescent galaxies have a much stronger build-up over time than star-forming galaxies. So that already shows you that the fraction of quenched galaxies increases dramatically over time. Another thing I would like to say at this point is that this is a field survey. And the field, I mean, throughout this talk, a representative part of the universe. So a part that includes all environments. So this is maybe a more familiar representation of the quenched fraction of galaxies as a function of stellar mass here on the x-axis and overdensity on the y-axis. So the field, as I said, includes this all, but you can split it up in density quartiles, for instance, which shows that galaxies are more likely to be quenched at high mass, and also at fixed stellar mass, they are more likely to be quenched in high density environments, of course, which is what we know. Now, mathematically, you can describe this quite well by two separate functions, one that depends only on mass and one that depends only on environment. And this was realized and worked out by in a paper by Peng et al. 2010. And the physical interpretation for this mathematical good representation is that that the mass axis, so mass-driven quenching, what he said, can be caused by AGM feedback, outflows from stellar winds, supernovae, gas exhaustion, and more likely in the overdense environments, there's gas starvation, strangulation by other galaxies, tidal stripping, mergers, ramp pressure stripping. So there's a lot of theoretical basis, physical basis behind this model, but the model itself is purely empirical. Now we can go out to clusters and groups and see how this excess quenching depends on redshift, for instance, and on the different halo masses. So here's a comparison between clusters and groups. Groups here in blue, clusters in gray. And even though this is a sort of a wild compilation of results that have come out in the literature by Julie Nanté a couple of years ago, there are a few trends that are already visible in this compilation. And that is that clusters seem to have a higher quenching efficiency than groups. So the gray points are in excess of the blue points. And also there seems to be an increase towards the local universe. Now this is still being discussed, and also will be discussed further in a talk by Andrew Reeves, I think later today. And one other thing I want to mention here, so we call this collectively within GoGreen quenched fraction excess, but there are several other names that were given to the same term in the literature, such as transition fraction, conversion fraction, and environmental quenching efficiency. These all essentially refer to the same measurement, which is shown here. Now this quenched fraction excess is very nice, but of course, if you look in detail, there is a dependence on potentially stellar mass. This is under discussion, and that may depend on the redshift. And also there is a dependence on radial distance. If you look only at the centers of the clusters and the groups, you may find a different quenched fraction excess than when you go out and probe also the surrounding areas. So this is the compilation of quench fractions and their derivatives. Let's go back now to the stellar mass function and see how this all fits together there. So this is the toy model that was introduced by Peng, and I think it's quite central to understanding the rest of this talk. So let me spend a few minutes on this. So two main physical, two main observables that drive this model is, first of all, that the specific star formation rate of star forming galaxies is not a strong function of mass and environment. And also that the stellar mass function of star forming galaxies, the shape of that remains roughly constant with time. So what that means is that basically if you look in this log plot, the first point tells you that if you don't do anything to a star forming population, you just have in situ star formation, and all star forming galaxies grow in stellar mass, roughly like the arrows here point out. But to keep the shape of the stellar mass function of star forming galaxies independently of time, which we also show in the field studies of the stellar mass function, you need to primarily quench galaxies at high mass. So this is what we call mass quenching or intrinsic quenching. So the quenching of these galaxies is higher at high mass or high at higher star formation rate, which is equivalent here. So that works quite well, this model, to reproduce the stellar mass function of central galaxies in Sloan. So that's here shown at the data points, split between red and blue galaxies. And the model shown here in the solid line reproduces the data very well. Now for the satellite galaxies, there's a different form, and that can also be understood in the same framework and also following the same observables. Namely, you can also quench galaxies completely independently of stellar mass. And that would lower the overall normalization of the star-forming galaxy stellar mass function, but not change its shape. And that is what you see here. So this upturn is caused by those galaxies that have been quenched completely independently of stellar mass. Now, this is all set up in the local universe and different environments, not really probing the clusters, and definitely not going up to clusters at high redshift. So to test whether this model also works in that regime, we have looked at G-class already several years ago, and Adam briefly showed the main results of the measured stellar mass function there. I just want to show one figure here to show you how this simple quenching model, empirical model, does in reproducing the stellar mass function of G-class, which is measured here and shown in the data points. And the model is are the red and the blue solid lines, where the red solid line is basically composed of a part that is mass quenched, so self-quenched, and a part that is environmentally quenched. So if you add them both together, you get this red solid line, And the point we made in this paper is that there is a mild to moderate tension, I would say, in the low mass end. So the expected number of quenched galaxies is higher than the actual number that we measure in the data. Now, of course, with GoGreen, we can explore exactly that regime because GoGreen has deeper photometry, deeper spectroscopy, so we can exactly test this regime better, where GoGreen stands out compared to G-class. Now, going very quickly over the GoGreen survey again, but this is of course what Mike already showed. Here is the large sample of 11 clusters, which we can all combine. The photometry, which ranges from B band all the way to mid of IRAC bands for all clusters. The photometry is complete down to about 10 to the 9.5 solar masses, a bit shallower from quiescent galaxies. And also with the photometry, we probe well beyond R200. Now, the trick is to do this properly and to measure the stellar mass function is to correct for completeness and to account for all galaxies, not just the galaxies that have been targeted spectroscopically. So this is described in quite some detail in this paper, but the goal is to use the depth of the photometry and to measure the stellar mass function all the way down to these limits. But as you can already see here in this figure, here in red and green are the spectroscopic targets. Of course, not all galaxies were targeted. That's impossible in any reasonable survey. So the spectroscopy is not fully complete down to this limit, but it is representative. So all galaxy types have been probed spectroscopically. So the trick for this paper is then to determine the membership for galaxies, the membership fraction of galaxies that have not been targeted spectroscopically based on similar galaxies that were targeted. And similar here meaning different criteria. So first of all, similar in photometric redshift, so they have to be at the redshift of the cluster. Similar in galaxy types, because there are maybe, especially for star-forming and quiescent galaxies, this is very different. Stellar mass, because the contrast of the cluster against the interlopers is a function of stellar mass, and also of cluster center distance. So the closer you are to the cluster, you're more likely to hit a cluster galaxy than when you go further out. So all this combined allows us to estimate which galaxies are actually part of the cluster and which are interlopers. Now, doing a sanity check is to compare it with a different method to determine membership. It has been used throughout the literature, and this is what we can do for the quiescent population, which is to make a purely statistical background subtraction. So this is not using any of the spectroscopy. This is purely based on the photometry and using a reference field from which we take a subset of filters, and we make sure that the noise properties are the same and do everything in an identical method between the cluster and the field, subtracting the expected interlopers, and you get essentially the same results here. So these are the two data points based on the two different methods. And the Schechter function fits here with their best fit parameters are compared and they're exactly the same. Okay, so let me go now to the main results. Again, for more details on the methodology, please look at this paper, or I'm happy to talk later. These are the main results here, comparing the GoGreen clusters within 1 megaparsec from the BCG to the field at the same redshifts. So here again, split between red and blue galaxies. And the lower panels are the quenched fractions in the different regimes, so the field and the cluster. Now, the first thing that may be observed is that the total stellar mass function, which is shown in black here, has a very different shape between the clusters and the field. So there's a clear excess of low mass galaxies in the field, which does not exist in the clusters. However, there is a much higher quenched fraction of galaxies in clusters than in the field. So that can also be seen here in the lower panels. But if you look just at the shape of the stellar mass function of quenched galaxies and between the cluster and the field, the shape seems to be roughly the same. Only the normalization is clearly different. And the same is true for the star-forming galaxies. one thing I have to say explicitly, and that's also what Michael showed in his talk, is that the division between star-forming and quiescent galaxies has been done based on their UVJ colors. So it also accounts for dust extinction. So this is the one way to look at the stellar mass function. Another way is to split them directly between galaxy types. So here is showing the same data, same information, but only for quenched galaxies between the cluster in red data points and the field, which has been renormalized to be able to directly compare the shapes. And what just appeared to be true in the previous panel is definitely more easy to see here, is that the shape of the stellar mass function of quenched galaxies is the same between the cluster and the field. And that can be seen here also in their best fit Schechter parameters. So we just were able to fit the data well with a single Schechter function. And the field and the cluster are described by the same function. And the same is true for the star-forming galaxies. So the star-forming galaxies have a similar shape and the stellar mass function between the cluster and the field. What is very different, again, is that of all galaxies. So if you combine all galaxies, the shape of the stellar mass function is dramatically different. And that's these three can only be true because there are many more quenched galaxies in the cluster compared to the field. Now let's take a look at that again and compare it to the local universe. So these are the quenched galaxies in the go-green clusters versus field. And this is the local universe as probed by Sloan in Peng's work. Here there's a division between density in the diamonds here are the lowest density quartile in our field sample, whereas the triangles are the highest density quartile in our field sample. So you can already see that the shape of those two stellar mass functions are different. So whereas there is this difference in the local universe, explained by the typical Peng style environmental quenching, this is not the case in the go-green sample. So this mass-independent environmental quenching works in the local universe, and it's expected to increase, of course, the overall quench fraction if you have an extra quenching term, but also it's expected to lead to a relative excess of low-mass quenched galaxies. And whereas the first is also observed for go-green, the second is definitely not. So that calls for a different way of quenching compared to the local universe. Another way of looking at that is actually, I'm going to skip this. This is not super interesting, and you're a bit lacking time here. So the question is, how can we reproduce this, the data points both in the low mass end and the high mass end, which is a quenching model? So that does not work. You cannot reproduce both the low mass and the high mass end of the stellar mass function by such a simple quenching model by Peng. So there clearly is a different quenching mechanism at play, a different redshift. And one hypothesis is that all galaxies at high redshift may quench via a similar intrinsically different process. So that would give you a stellar mass function of quenched galaxies that is just change the normalization between the cluster and the field, but there is no different shape. This is one hypothesis. It's basically the quenched, the model introduced by Peng, which I reproduced and started at different redshifts to see if there may be a early formation of proto-cluster galaxies compared to the field, and that this may be responsible for a higher quench fraction. So basically start forming galaxies earlier, and therefore by the time you observe them, which is in this instance redshift 1.2, which is the go-green redshift, you would have a higher quenched fraction because you started earlier than when you start, say, at redshift 4. So there's only a 1 gigayear delay here in the start of galaxy formation, but you can already have a much higher quench fraction in the left panel here than in the right panel. And this is to compare that to the quench fraction axis, which you measured in go-green here in the black and the gray data points. And indeed, the qualitative shape that you get in such a very simple galaxy formation model roughly reproduces the trend that we observe in the data. And this is, of course, a very simple quenching rate that is proportional to the star formation rate, as in Peng. It's not a physical model, I would like to stress again. But there is also a physical model which we have explored in this paper that Sean McGee popularized in 2014. It's based on cosmic starvation, and he called that overconsumption. So the basic idea is that you have a halo here with potentially a central galaxy at its center, and galaxies before they are accreted by this halo are still accreting gas from the cosmic web. But when they are accreted by the halo and are seizing that cosmic web gas accretion, they can only consume their own ISM gas and drive outflows, which will ultimately quench them. But because the star formation rate of high mass star forming galaxies is higher than that of low mass galaxies, they have a shorter gas consumption timescale, and therefore they run out of gas more quickly than their low mass counterpart. And that can introduce that mass-dependent environmental quenching, which we observe in the data. So that may be very efficient, especially at high redshift, where the star formation rates are relatively higher than at low redshift. So this may be one of the key driving mechanisms of environmental quenching at high redshift, whereas at low redshift, we observe more RAM pressure stripping kind of quenching in addition to this. Okay, I'm definitely running out of time now, so let me just quickly summarize what I mentioned here. So quenching is already barely understood, as Michael pointed out, even at low redshift. And at redshift higher than 1, it seems to be even stranger because it looks very different from the local universe. So the stellar mass function of star-forming galaxies has an indistinguishable shape between the cluster and the field. And the same is true, which is strange because this is not the case in low redshift for the quiescent galaxies. So even though the shapes are the same, there is a highly elevated quench fraction in the clusters at high redshift, and this may indicate a different process of quenching than at redshift 0. So there are several interpretations possible. I quickly mentioned that Peng can solve this by creating a head start of galaxies in clusters compared to the field, a head start or acceleration of intrinsically driven quenching. It's also possible that a form of cosmic starvation or overconsumption creates the dependence on stellar mass that we need in the environmental quenching. Now, there are some complementary probes to test this, and that's exactly going to be the topic of the next 2 talks. So I'd like to give it to the next speakers, and thank you for your attention.